The process begins with straightening rolling, where the raw metal sheet is passed through a series of rollers. This step removes any warping or bending in the material, ensuring a flat and uniform base for further processing. Proper straightening is critical to maintaining dimensional accuracy throughout the manufacturing process. Once the raw metal sheet has been straightened and flattened, the next crucial step is laser cutting. This process uses a high-powered CNC-controlled laser to precisely cut out the circular shape of the saw blade. The laser emits a focused beam of intense heat, which melts, burns, or vaporizes the metal, creating clean and accurate cuts without physical contact. Beyond cutting the basic circular outline, the laser also creates slots, expansion gaps, and noise reduction features. These design elements help manage heat buildup, reduce vibration, and improve cutting stability. The non-contact nature of laser cutting prevents mechanical stress on the metal, preserving its integrity. Compared to traditional mechanical cutting, laser cutting offers exceptional accuracy, minimal material waste, and smooth edges. The process is highly efficient, allowing for mass production with consistent quality. After laser cutting, the saw blade moves on to heat treatment to enhance its hardness and durability. The cut saw blade then undergoes heat treatment, where it is exposed to high temperatures to modify its microstructure. This process increases the blade's hardness and strength, making it more resistant to wear and deformation during use. After heat treatment, the blade is subjected to tempering, which involves reheating it to a controlled temperature and then slowly cooling it down. This process reduces internal stresses and increases toughness, preventing brittleness and ensuring the blade can withstand high-speed operation without breaking. Milling is used to refine certain features of the blade, such as adding precision grooves or surface modifications. This step ensures that the blade maintains a balanced design, which is crucial for minimizing vibration during operation. To achieve a smooth surface, the blade undergoes grinding and polishing. This process removes burrs, sharp edges, and surface imperfections left from previous steps. A polished surface not only improves the blade's aesthetics, but also reduces friction, leading to smoother cutting performance. Before a circular saw blade reaches the market, it undergoes rigorous pre-market testing to ensure quality, durability, and performance. The testing process begins with a dimensional inspection, where the blade's diameter, thickness, and bore size are measured for accuracy. Next, the blade undergoes a balance test to check for any imbalances that could cause excessive vibration during use. A hardness test follows, verifying that the heat treatment and tempering process have achieved the desired strength and toughness. For cutting performance, real-world cutting tests are conducted on various materials, such as wood, metal, or plastic, depending on the blade's intended use. This helps assess sharpness, precision, and wear resistance. Additional tests include coating adhesion, corrosion resistance, and noise reduction evaluations. Only after passing these strict quality control checks is the saw blade approved for packaging and distribution, ensuring reliability and safety for end users. Earthing or grounding is a critical component in electrical safety, protecting structures, equipment, and individuals from electrical faults. One effective method of establishing a robust and long-lasting earthing system is through CAD welding, also known as exothermic welding. When dealing with 300 mm cross-earthing wire, CAD welding ensures a secure and highly conductive connection, making it an essential technique in grounding systems. CAD welding, or exothermic welding, is a process that creates a permanent molecular bond between conductors using a high-temperature chemical reaction. The reaction takes place in a graphite mold, where a controlled exothermic reaction melts metal powder to fuse the conductors together. This technique is widely used for earthing and lightning protection systems due to its superior conductivity, durability, and resistance to environmental conditions. Importance of CAD welding for 300 mm. Cross-earthing wire. A 300 mm cross-earthing wire refers to a copper or aluminum conductor with a 300 square millimeters cross-sectional area, typically used in grounding applications. This large conductor size is necessary for high-power applications, substations, power plants, and industrial facilities, where significant fault currents must be safely dissipated into the ground. Low electrical resistance. The exothermic reaction creates a solid-state connection with no mechanical joints, reducing resistance and improving efficiency. Corrosion resistance. Unlike bolted or clamped connections, CAD welded joints do not loosen or degrade over time, providing long-term reliability. High strength and durability. The molecular bond is stronger than the conductors themselves, making it resistant to mechanical stress and environmental factors. Maintenance-free connections. Since there are no bolts or screws, there is no need for periodic tightening or inspections. CAD welding process for 300 mm. Cross-earthing wire preparation. Clean the conductor surfaces to remove dirt, oxidation, and contaminants. Mold setup. Place the earthing wires inside a specialized graphite mold designed for cross connections. Charge the weld powder. Insert the CAD welding powder into the mold and position the ignition disc. Ignition and welding. Ignite the powder using a flint igniter or electronic igniter. The reaction melts the conductors, forming a seamless joint. Cooling and finishing. Allow the weld to cool, then remove the mold and inspect the joint for integrity. Applications of 300 mm cross-CAD welded earthing wire, electrical substations, power transmission and distribution systems, lightning protection systems, railway and metro grounding industrial and commercial buildings. By using CAD welding for 300 mm cross-earthing wires, electrical engineers ensure a highly efficient, long-lasting, and maintenance-free grounding system, improving overall electrical safety and performance.
The rolling process for the steel plates is a crucial step in manufacturing wind towers. Plate rolling machines, also known as plate rollers or plate bending machines, are utilized for this purpose. These machines are designed to shape and bend the steel plates into the required cylindrical shape. During the rolling process, the steel plates are carefully positioned and fed through the rollers of the machine. The pressure exerted by the rollers causes the plates to gradually curve and take on the desired cylindrical form. The plates may need to be passed through the rollers multiple times, adjusting the position and pressure each time to achieve the precise diameter and thickness specified in the wind tower design. Skilled operators monitor the rolling process closely, ensuring that the plates are properly aligned and evenly rolled. They adjust the machine settings as necessary to achieve uniformity and maintain the structural integrity of the plates. The accuracy and precision of the rolling process are essential to ensure that the resulting cylindrical sections of the wind tower are of the correct dimensions and can be seamlessly welded together in the subsequent stages of manufacturing. By employing plate rolling machines, manufacturers can effectively shape the steel plates and prepare them for the welding and fabrication processes that follow. This step plays a significant role in creating the cylindrical structure of the wind tower, providing the foundation for its strength and stability. After the steel plates have undergone the rolling process, they are ready to be welded together to form the main cylindrical structure of the wind tower. Welding is a critical step that requires skilled welders and precise techniques to ensure the integrity and strength of the final product. Commonly used welding methods in wind tower manufacturing include submerged arc welding (SAW) and gas metal arc welding (GMAW). These methods offer high efficiency and produce reliable welds. SAW involves the formation of a weld through an electric arc generated between a continuously fed wire electrode and the workpiece, while GMAW utilizes a similar concept, but with the addition of a shielding gas to protect the weld area from atmospheric contamination. Skilled welders carefully position the rolled plates and apply the appropriate welding technique, They follow the specified welding procedures, ensuring proper joint preparation, correct heat input, and adequate filler material. Welding parameters such as current, voltage, and travel speed are meticulously controlled to achieve optimal penetration and fusion. During the welding process, welders employ non-destructive testing techniques, such as ultrasonic testing and X-ray inspection, to verify the quality of the welds. To protect the tower from corrosion and enhance its lifespan, surface treatment processes are applied. The tower undergoes abrasive blasting to remove any impurities or rust from the surface. Then, a primer coating is applied to prevent corrosion, followed by an outer layer of paint for aesthetics and further protection. Once the tower structure is complete, internal components are installed. This includes the ladder system for accessing the turbine, electrical conduits for wiring, and any necessary platforms for maintenance and inspection purposes. These components are securely attached to the tower, ensuring structural integrity. After passing quality inspections, the wind tower is prepared for transportation to the wind farm site. Due to their large size, towers are typically transported in sections and assembled on site using specialized cranes and equipment. The tower is securely anchored to the foundation, ensuring stability and safety. Once the wind tower is installed, regular maintenance and inspection are essential to ensure optimal performance and longevity. This includes visual inspections, corrosion monitoring, and structural assessments. In the first stage of the manufacturing process of seamless steel tubes, the basic input material is steel scrap. Steel scrap is sourced from various locations and collected for further processing. At an authorized recycling center, the steel scrap undergoes separation to remove impurities. Liquids, such as oils and coolant, are drained from scrap cars, while non-ferrous materials like plastic and glass are carefully disposed of. This separation process ensures that the steel scrap is clean and suitable for the subsequent stages of production. By eliminating contaminants, the resulting steel material maintains high quality and integrity throughout the manufacturing process. After the separation process, the clean steel scrap is ready for further processing in an electric arc furnace. The electric arc furnace is a vital component in the manufacturing of seamless steel tubes. It is capable of melting large quantities of steel scrap at high temperatures to produce molten steel. The electric arc furnace has an impressive capacity, with the ability to melt up to 60 tons of scrap per hour. This makes it a highly efficient and productive part of the production process. To achieve the necessary temperatures, the electric arc furnace can reach up to 1620 degrees Celsius. Once the steel scrap is inside the electric arc furnace, an electric arc is generated, providing the necessary heat to melt the scrap. The intense heat causes the steel scrap to liquefy, resulting in a pool of molten steel. The molten steel is then transferred into a ladle, which acts as a temporary container. At this stage, additives are introduced for primary alloying. These additives are carefully selected based on the desired properties of the final product. Alloying elements such as chromium, nickel, manganese, and others are added to achieve specific characteristics, such as improved strength, corrosion resistance, or heat resistance. The ladle containing the molten steel and alloying additives is transported to a ladle furnace. In the ladle furnace, additional alloying elements are added to fine-tune the composition of the steel and ensure it meets the desired quality standards. The ladle furnace allows for precise control over the alloying process, enabling manufacturers to achieve the desired chemical composition and properties of the steel. The combination of the electric arc furnace and ladle furnace ensures that the molten steel undergoes thorough alloying, resulting in a high-quality and well-controlled steel composition. This step is crucial in determining the final characteristics and performance of the seamless steel tubes. When the molten steel is ready, it is continuously cast into expansion bars with the square cross-section. The choice of cross-section depends on the specific requirements of the final product. After casting, the blooms undergo cutting, marking, and cooling processes to prepare them for further processing. Quality control checks are carried out to ensure the integrity and specifications of the blooms. The blooms are then transferred to a two-rolling mill, where they undergo further processing. The two-rolling mill reduces the size of the steel blooms, gradually transforming them into tubes with smaller cross-sections through a series of rolling operations. To achieve the desired dimensions for the seamless steel tubes, the steel blocks, which have been previously cut to the desired length, undergo further processing. First, the blocks need to be heated to the rolling temperature to make them malleable. This is done in a rotary furnace where the blocks are heated uniformly. Once heated, the blocks are ready to be formed into circular molds. This is accomplished using a piercing press. The blocks are placed in the press, where a punch pierces through the center, creating a hollow cavity. The blocks are transformed into circular molds with the central hole, which will eventually become the inner diameter of the tubes. The circular molds, or billets, are then fed into a mill for elongation and processing. This mill is designed to stretch and shape the billets into longer lengths. As the billets pass through the mill, they undergo a series of rolling operations. These operations gradually reduce the outer diameter of the billets while increasing their length. The process is repeated several times until the desired dimensions are achieved. After the elongation process, the semi-finished tubes undergo milling to remove any surface defects or irregularities. This ensures that the tubes have a smooth and uniform surface. The next step is rolling the semi-finished tubes in a drawing reduction belt. This process further reduces the outer diameter of the tubes and brings them closer to their final dimensions. The drawing reduction belt consists of a series of rollers that exert pressure on the tubes, causing them to be elongated and reducing their diameter. This process is repeated until the tubes reach the desired dimensions. Throughout the entire process, careful monitoring and quality control checks are carried out to ensure that the tubes meet the required specifications. Any defects or deviations from the desired dimensions are identified and addressed. Once the tubes have reached the desired dimensions, they are ready for further processing or finalization. This may include heat treatment, additional shaping, or surface treatments depending on the specific requirements of the end product. After the tubes have been rolled to the desired dimensions, they undergo a cooling process to stabilize their structure. Once cooled, the tubes are cut to the requested length using hydraulic shears or a slitting saw. Quality control checks are conducted to ensure the tubes meet the required standards and specifications. The ends of the tubes are smoothed to remove any rough edges or burrs. The tubes are then labeled, packaged, and undergo any additional final operations as specified by the customer, such as surface treatments or specific markings. These final steps ensure that the tubes are ready for shipment and meet the customer's requirements. This process involves drawing the tubes through die plates or mandrels to achieve specific dimensions. To restore the required mechanical properties, annealing in a continuous annealing furnace is necessary. In the finalization stage of the manufacturing process, several important operations are carried out to ensure the seamless steel tubes meet the required standards before they are shipped to customers. Firstly, non-destructive testing is conducted on the tubes to identify any potential defects or flaws that may affect their performance or structural integrity. This testing method helps to ensure that only tubes of the highest quality are selected for further processing. Next, the tubes are cut to their final specified length. This step involves precise cutting techniques, such as hydraulic shears or other cutting methods, to achieve the desired length accurately. After cutting, a thorough visual inspection is performed to verify the dimensions and external appearance of the tubes. This inspection ensures that the tubes meet the required tolerances and have a visually appealing surface finish.
The convergence of innovative technologies is transforming the construction industry, and one of the remarkable innovations at the forefront is the integration of the Max-Truder system within innovative precast concrete factories. This synergy is revolutionizing the production of precast concrete elements, offering unparalleled precision, efficiency, and flexibility in construction processes. The Max-Truder system is a state-of-the-art extrusion technology that has found its application in various industries, including construction. When integrated into an innovative precast concrete factory, it becomes a game-changer by allowing for the extrusion of concrete in complex shapes, intricate designs, and customized profiles. High-performance extruder. The Max-Truder system includes a high-performance extruder specifically tailored for concrete applications. This extruder is equipped with advanced controls for precise material flow, mixing, and consistency, ensuring the highest quality concrete elements. Customizable extrusion dies. One of the standout features of the Max-Truder system is its ability to use customizable extrusion dies. These dies can be designed to produce a wide range of concrete profiles, from simple beams and columns to highly intricate facades and architectural details. This flexibility is invaluable in meeting the diverse needs of construction projects. Digital design integration. Innovative precast concrete factories leverage digital design and modeling software to create precise 3D models of the desired concrete elements. These digital designs are seamlessly integrated into the Max-Truder system, ensuring that the extrusion process aligns perfectly with the project's requirements. Material handling and mixing. The Max-Truder system includes material handling and mixing units optimized for concrete. These units ensure that the concrete mixture is well prepared, homogeneous, and ready for extrusion, contributing to the structural integrity and aesthetics of the final product. The Max-Truder system brings a myriad of benefits to the innovative precast concrete factory, and its applications span various construction sectors. Architectural precast elements. In architectural concrete, the Max-Truder system excels in producing intricate facades, decorative panels, and custom-designed elements that enhance the aesthetic appeal of buildings. Structural components. Precast concrete structural elements, such as beams, columns, and wall panels, benefit from the precision and consistency offered by the Max-Truder. This ensures the structural integrity and load-bearing capacity of the finished products. Infrastructure projects. The technology finds extensive use in infrastructure projects, including the production of precast bridge components, tunnel segments, and sound barriers, thanks to its ability to meet stringent quality standards. Sustainable building. The Max-Truder system is also conducive to sustainable building practices. It can extrude concrete elements using eco-friendly and recycled materials, contributing to reduced environmental impact in construction. Advantages of Max-Truder in precast concrete manufacturing. The integration of the Max-Truder system into innovative precast concrete factories offers several compelling advantages. Design freedom. The ability to create custom profiles and intricate designs enables architects and designers to explore new creative possibilities, resulting in unique and visually striking structures. Precision and consistency. The Max-Truder ensures that each extruded concrete element meets precise dimensional and quality standards, reducing the need for costly rework and minimizing waste. Efficiency. The automation and digital integration of the system streamline the production process, reducing labor costs and accelerating project timelines. Sustainability. The ability to use sustainable materials and minimize waste aligns with the construction industry's growing emphasis on eco-friendly practices. Cost savings. The precision and efficiency of the Max-Truder contribute to cost savings in both material and labor, making precast concrete elements more competitive in the construction market.
The ROTHO curing system at Solitaire Pavcon boasts impressive capacity, featuring 5 double chambers with a total capacity of 2,000 pallets. This substantial capacity allows for the simultaneous curing of a large volume of concrete blocks and pavers, contributing to increased productivity and efficiency in the production process. The production process for the curing system, designed for fly ash brick production at Solitaire Pavcon in India, is a crucial aspect of ensuring the quality and durability of concrete blocks and pavers. This innovative curing system, known as ROTHO, stands out due to its features and efficient production capabilities. One of the key strengths of this curing system is its hot dip galvanized steel construction. This construction material is chosen for its exceptional durability and resistance to corrosion. In the demanding environment of concrete block and paver production, where exposure to moisture and chemicals is common, the use of galvanized steel ensures that the curing chambers remain structurally sound over time. This durability is essential for the long-term reliability of the curing system. A central component of the ROTHO curing system is its advanced air circulation system. Proper curing is essential for the development of concrete block and paver strength and durability. The air circulation system within this curing system ensures uniform curing conditions throughout the chambers. It promotes consistent temperature and humidity levels, allowing the concrete products to cure evenly and thoroughly. This precise control over the curing environment is vital for achieving the desired properties in the final products. Another noteworthy feature of the ROTHO curing system is its isolated roller shutter doors. These doors play a crucial role in maintaining the controlled curing environment within the chambers. By isolating the curing chambers from external factors, such as temperature fluctuations and dust, these doors help ensure that the curing conditions remain stable and optimal. This level of control is essential for producing high-quality concrete blocks and pavers consistently.
The casting process initiates by transferring the molten metal from the ladle into the tundish, which can hold approximately 28 tons of liquid steel. Once in the tundish, the steel flows through a submerged entry nozzle, which acts as a conduit, transporting the molten metal into the mold, where it takes the desired shape. To ensure high surface quality, hydraulic resonance oscillator is used within the mold. The caster's strand guide system, consisting of 8 segments, allows for the production of steel with high cleanliness and a homogeneous internal microstructure. The integrated air mist cooling system, which utilizes an air-water mixture, achieves uniform cooling rates, contributing to the desired metallurgical properties. The primary and secondary torch cutters ensure optimal slab lengths for subsequent processing in the rolling mill. A large crane is employed to transport the slabs within the facility. SMS Group provided the entire caster, including mechanical components, hydraulic systems, environmental and auxiliary facilities, as well as the comprehensive electrical and automation package. The caster at Puyan Steel is a highly efficient system with an impressive production capacity of 1.2 million metric tons of slabs per year. These slabs exhibit a range of dimensions, including thicknesses between 150 and 180 millimeters, width spanning from 1,000 to 2,300 millimeters, and lengths varying from 2.18 to 3.5 meters. The primary and secondary torch cutters ensure optimal slab lengths for subsequent processing in the rolling mill. A large crane is employed to transport the slabs within the facility. The single furnace upcast manufacturing process begins with the copper melting stage. Raw copper material, typically in the form of copper cathodes or copper scrap, is introduced into the furnace. The furnace is designed to generate high temperatures that can melt the copper and transform it into a liquid state. The molten copper is maintained at a specific temperature range to ensure its liquidity and facilitate further processing. Once the copper is melted, the next step is to hold the liquid copper in the furnace. This holding phase is crucial for maintaining the desired temperature and liquidity of the molten copper. It allows for a consistent supply of copper to be fed into the subsequent stages of the manufacturing process. After holding the liquid copper, the molten metal is then directed into the upcast wire casting system. The upcast technology utilizes an upward continuous casting method where the molten copper is poured into a water-cooled mold. As the copper exits the mold, it solidifies into a continuous strand, forming a high-quality copper wire. The casting system is designed to control the cooling rate and optimize the wire's diameter and properties. The newly formed copper wire goes through a cooling and elongation process. It passes through a series of water-cooled wheels, or dies, which gradually reduce the wire's diameter and elongate it.